Hey, ladies and gentlemen, I'm back for a second part of 9.8 on cell potential and free energy. So here we're really going to focus on linking voltage of an electrochemical cell to the thermodynamic favorability of that cell operating. So this is the same set of slides. We're going to be focusing more on this portion of the curriculum. So looking at Gibbs free energy and its relationship to cell potentials. So I'm going to zip ahead to where we left off before. This is just kind of like an overview. A cell with a positive cell potential is a thermodynamically favorable reaction. If it's negative, it's unfavorable. Gibbs free energy is related to this as well. And it's also tied into the number of moles of electrons transferred. So you need to know how many, if you look at the balanced equation, how many moles of electrons were involved in the redox process. There is a link between these, and that link is called Faraday's constant, and it's the amount of charge that is available per moles of electrons. This number is on your reference sheet, 96,485 coulombs per mole of electrons. The equation that you'll be using for this is on the reference sheet as well in your section for thermodynamics. So we have multiple ways of calculating delta G. We looked at this one back in Unit 6. We looked at this one in the beginning of this last part of Unit 9. And now we're looking at this one more specifically. So we can link these equations together and use them to figure out a bunch of stuff because math. The deal with this equation, this last one that we're looking at right now, is it gives us an experimental means of calculating delta G. The other stuff we're looking up on tables and such. This is going to give us, we can get a voltage off of an actual experimental apparatus and use that to calculate delta G. This is pretty much the same stuff that was just on that prior slide. Okay, same deal here. All right, so let's look at an example problem. We want to calculate delta G for this reaction. Is it spontaneous? Which thing is the cathode? Calculate K. Look at our look at these half reactions, calculate cell potential. So we have a lot of stuff going on here, okay? So this question here is really the first thing we can look at, which is the cathode. So we're given this equation here. We can look and see what thing is being reduced. So what's being reduced here? The copper electrode is the cathode. All right, so now is it spontaneous? How am I going to determine if this is spontaneous or not? We have to calculate delta G. We could also calculate a voltage instead. Okay, so let's look at the voltage. We need the voltage first. So we have these half reactions that I just took off of a table. I have the voltage associated with each of these reduction half reactions. So when I have the more positive reduction potential, that's the one that is actually undergoing reduction, which is what is going on here. Okay, so the cell potential is going to be the one that gets reduced plus the one that gets oxidized after I flip its sign. So 0.34 plus positive 0.44, because that thing actually gets oxidized, not reduced. So the voltage of this cell is a positive 0.78 volts. What does that tell us about the thermodynamic favorability? It is. Now I'm going to verify that by calculating delta G. I'm going to calculate delta G using this equation. So delta G equals negative NFE. So negative. Now, how many moles of electrons were involved in this balanced equation? Well, it's balanced already. So there's 2 moles of electrons being gained by the copper. There's 2 moles of electrons being lost by the iron. So the number of moles of electrons, is 2. So N is equal to 2. We get that from the balanced equation. Faraday's constant, I'm going to put the moles here, 2 moles of electrons. Faraday's constant, 96485 coulombs per mole. Times the cell potential, the voltage we just calculated is 0.78 volts. Now, units wise, putting volts here isn't going to help us cancel anything out. We have coulombs here, and we know that delta G involves joules or kilojoules. The unit of volts is also equal to joules per coulomb. So I can use that as my conversion factor. So when I calculate this, this gives me a negative 150,516.6, and that's going to be in joules. So look at my signs here. I have a negative sign here. The voltage was positive, so that means my delta G is going to be a negative number. Is a negative delta G favorable? Yes, it is. So this is in joules. Sometimes they'll tell you like calculate it in kilojoules, so you would just convert it to negative 150.5 or so kilojoules. Now it says calculate K. So do we have a relationship between delta G and K? Yes, we do. Delta G is equal to negative RT ln K. Now, looking at what we've already done, we have a positive voltage, thermodynamically favorable. We have a negative delta G, thermodynamically favorable. So let's talk about what the magnitude of K should be. Should K be a number greater than 1 or less than 1? Well, greater than 1 means it's products favored. Less than 1 means it's reactant favored. So since we're talking about a forward process that is happening, we should have a pretty decently sized number, at least bigger than 1 here for K when we're done. Now, also important here, units. The R value that we're going to be using is that 8.314, and that involves joules, not kilojoules. So I'm going to go back to this delta G number and use the joules version of it. So that's negative, let me put this all back up here, negative 150,516.6, and that I'm going to keep in joules, negative RT ln K. All right, so when I take all this stuff and divide it out, natural log of K, look what happens to my signs. I'm getting a positive number here. That's going to be 60.75 or so. How do I undo this natural log? I have to do e to the 60.75 power, which is equal to 2.42 times 10 to the 26th power. Does that give me a big value for K? Yes, it does. All of these things are related now. Look at the values that we're working with. This is another example problem that I have it broken down into a couple slides so we can look through the different portions of the question. So we're given this electrochemical cell. We're told the direction of electron flow. We're given half reactions for this. So we're going to be going through all right, so this is the breakdown of the question. I just chopped it apart so we can just work with the pieces that we need. So part A, write the balanced equation for the reaction occurring in the cell, determine the standard cell potential, and what happens to the concentration of aluminum ions, and explain your answers. So to write the balanced equation, we have to first determine what is really undergoing oxidation and reduction here, and then figure out how to balance our electrons. So we look at our voltages. The more positive voltage is the one is actually going through reduction, and the one with a less positive voltage is going through oxidation. So its half reaction has to be reversed. When I do this, I also have to keep in mind the number of electrons that are lost and the number of electrons that are gained. Those numbers have to be balanced out. So I need to multiply all of this iron stuff by 3 and all of this aluminum stuff by 2 to get my number of electrons equal to 6 on both sides. So my balanced equation, I'm going to keep the iron in the sequence that it's in, applying that 3 coefficient. I'm not going to write in the electrons this time because they're going to cancel out. So I have the 2 aluminums. Oh, I have to reverse that reaction, right? Because this one gets flipped around. And then I have the 3 iron atoms, and I have 2 positive 3, oops, what did I just do here? Positive 3 aluminum ions. Determine the standard cell potential. So the cell potential is going to be equal to the one that's getting reduced plus the one that's getting oxidized after I flip its sign. So that's negative 0.45 plus, now I've got to flip the sign of that, positive 1.66. So negative 0.45 plus 1.66. And the voltage of this cell is 1.21 volts. Does the concentration of aluminum ions in the solution increase, decrease, or remain the same as the cell operates? So I'm going to go back to this picture. So it's asking about this concentration. So we determined that the aluminum solid is going to undergo oxidation because it does not have the more positive reduction potential. So it's going to lose these electrons. So as the aluminum loses electrons, ions form. Well, what happens to those ions? They fall into the solution. So what's going to happen to the concentration of aluminum ions as this cell operates? That concentration is going to increase as those aluminum ions get dumped into the solution. So how can you answer that? You can say the concentration increases as the aluminum electrode oxidizes and the aluminum ions dissolve. Perfectly fine. Calculate the standard free energy of reaction, and is the value of K greater than, less than, or equal to 1? And explain your answers. So calculate for part D. Part E, we can either we can explain this theory based, or you can give the numbers if you want. It doesn't specify, but part D, we have to give an actual number. So we have different options for delta G, right? We have delta H minus T delta S. We have negative RT ln K, and we have negative NFE. We also have that summation equation. But so what applies here? Well, what information do we have? We do not have any information about delta H or delta S. We do not have a delta K value, so we can't use that second equation. We do not have a table of free energies of formation, so we can't use that equation. What do we have? We have a voltage. We know how many electrons because we have a balanced equation, and we can look up Faraday's constant. So we're going to use delta G equals negative NFE for this question. So the number of moles of electrons that are involved that we already figured out is going to be 6. So N is equal to 6. Faraday's constant, 96485. And the voltage that we calculated on the prior page was 1.21 volts. Plug all that in, negative 6 times 96485 times 1.21. And we got negative 481.1. And that's going to be in joules, because again, volts is going to be joules per coulomb. All of those units are going to cancel out. So that's our delta G value. If we're told to give it in kilojoules, make sure you do that. Okay, so we have a negative value. So all of this stuff should line up for you. If you have a positive voltage, it should be a negative delta G, because both of those indicate a thermodynamically favorable process. Now to answer E, is the value for K going to be greater than, less than, or equal to 1? If we want to answer this without using math, you could say it's going to be greater than 1 because a positive cell potential and negative delta G both indicate a thermodynamically favorable process, which means products will form. And since K is equal to the concentration of products over the concentration of reactants, your numerator is going to be large, which is going to mean that's bigger than 1. But, you know, I'd like to justify it with math because we can. Because we have the delta G value, we can use this equation, the second one here. Delta G equals negative RT natural log of K. So we're going to use the joules version of delta G because the R that we're using involves joules. I can't help you with units, guys. You really have to be careful with that. You're not going to be shown any mercy in grading if you're not keeping your units straight. They are provided to you. You need to use them. Okay, please, please, please be careful with that. 25 degrees Celsius is 298 Kelvin, natural log of K. So right away, you should see here, we have the negative sign on both sides, right? So that's all going to work out for us. So we're going to divide that 700,000, negative 700,000, by the product of the 8.314 times the 298. Natural log of K is equal to 282.7. So we're going to do e to that number. And we will get e to the 282.7. Oh, I got an overflow error message because that value is so huge when I just put this into my calculator. So, I mean, this number is going to be so large that I guess justifying this without math would work better for you. So if you get an overflow message like that, if you did plug it into the calculator, you could address that as well. This is a summary of what we're looking at here. In terms of looking at a reaction as thermodynamically favorable process or unfavorable process, a negative delta G, a positive voltage, product favored K, not spontaneous or unfavorable is going to be all the opposite of that. And we have, lots of different ways to find Gibbs free energy. So hopefully that's a nice link of all of those things for you. The last two lessons are going to look at what happens if we're not under standard